Hello and welcome, everyone. There's one person here. We started in our new textbook. We changed gears, and just as some quick review, oops, because it was just on Tuesday. But we talked about, okay, so what are some of the things that we'll be doing? Well, we want to learn from data, right? And so, and that's really broad. So sometimes we'll want to predict things, and sometimes we'll want to do inference. So hypothesis testing, for example, or confidence intervals where we're learning about the data, right? And so we can do predictions versus inference, right? And then we said, oh, I can't remember. Let me go back there. Now I really can't remember. Okay. There was something here that I wanted to mention. Blah, 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 blah. Okay, I think I got it. We want to build a model that minimizes the error, right? So we want to build a model that minimizes the error, without overfitting, right? And so we talked about overfitting. Overfitting is when you've got way too many terms in your model and it's relying too heavily on the sample data. So we want to build a model that minimizes the error without overfitting. Because when we're overfitting, right, a model that relies too heavily on sample data. So a model that relies too heavily on the sample and doesn't necessarily translate well to another sample, right? So, and doesn't necessarily translate to another sample. Okay. So that's kind of where we ended off last day, and we talked about some other stuff too, but that's the meat and potatoes of it. And so today we're just going to talk about, okay, well, if our goal is to build a model that minimizes the error, then what are we measuring? So we want to talk about the different error rates. We also talked about how regression, we use the term regression to talk about numerical outcomes. And then we said, okay, if we have a categorical outcome, then we're going to call it a classification. But it's really the same thing. It's just talking about two different outcomes. And so if the outcome, which is your y, is numerical, we typically call the modeling techniques regression. Call the modeling techniques, regression. Whereas if the outcome is categorical, and depending on kind of where and with who you took stat 230, numerical is of course qualitative. Of course, I said it wrong, quantitative, because it's a quantity, quantitative, and categorical is qualitative. Can't believe I mixed those two up. Well, I can actually, qualitative. So if the outcome is qualitative or categorical, then we call the modeling techniques, classification. Okay. That's kind of part of the review, but here it is explicitly. And so depending on if we're doing regression or if we're doing a classification, how we measure the error depends on how we're modeling. So how we measure error, depends on whether we're doing a regression model or a classification model, on whether we are doing a regression model, a regression, or a classification model, I'll say. Oh. So we'll start with regression model. So the regression model, we know about the residuals, right? Because we've talked about regression, and so or about regression, and so you've got your model, which in the simplest case is a straight line, and then you've got your data points that are hovering around that line. So and of course there's some error there. Okay, and so if we have a numerical outcome, then we can just calculate the error. Okay. So in the regression, right, which implies that we have a numerical outcome. Okay, but for regression, we measure the mean squared error. We try to minimize the mean squared error, which is the MSE. Now we can calculate the MSE. The MSE, and I'm going to add a page. I've got some, I wanted to explain those graphs in the textbook a little bit more because they take a little bit to wrap your head around, but I'll keep them down low. So the mean squared error is the sum from I equals 1 to n of yi minus the estimate at xi squared over n. Right? Basically the average of the residuals squared. Right? So here, this is the observed y, and this is the predicted y. And then we square them, because then if we added up positives and negatives, then how we found the model is by minimizing the residuals, so they would add to 0, right? And so that's why we have to square them so that we can see all of them adding together, and then that's a measure of the total error, and then we divide by however many residuals we have. Okay. And so this is the average residual squared. So that's one way that we could measure, how well our model fits our data. One problem becomes, okay, so I've got the data that I built my model on, and that's called our training data, whereas I want to apply it to future data, and that's going to be called our test data. Okay, and so when we build models, we build them using test data, or sorry, mixing up really critical words here. We build them using training data because we're training our model using training data. But the goal is to apply the model and have it perform well on test data. But we want to apply the model to test data. Okay. So the problem becomes, well, if we have our training data, right? So our actual data set, then I can model that data really, really, really well, right? But then if I take that model and I apply it to the test data, then what happens sometimes is maybe I overfit my model on my training data, right? And so now it really doesn't fit the test data. Okay, so usually what we do is we separate. So if we have a sample, a total sample size, then we would split our sample into test data and training data. We'd build our model on the training data, and then we test it on the test data, right? How well is it performing? Okay, that's not always possible, right? Because what if we want to be forecasting values? Right. So then I don't know how the stocks are going to perform next week. Right. All I know is how they're performing right now. And so I'd have to build my model off of that. And then I guess wait and see to find out how well my model did. Okay. So it's not always possible to have test data. Right. But we often split our sample into training data and test data. And test data. Okay. That's called cross-validation. Okay. And we build our model on the training data. Right? And then we check the model, we check the error of the model using the test data. Okay? So we build the model. We build the model on the training data. Then we measure the error on the test data. Then we measure the error on the test data. So we're going to talk about flexibility in models. And so a flexibility measure is the degrees of freedom. So it's really how many things am I estimating? Okay, so in the simplest case, right, a simple linear regression, I have a slope and I have an intercept, right? So I'm estimating two things. Okay, but then I could add on things to make my model more complicated. Okay, and so we can increase the flexibility of our model by increasing the number of things that we take into account. Okay, and so flexibility in the model, oops. That doesn't, I'll start over there. Yikes. Flexibility, oops, in a model refers to the number of coefficients that are being estimated. Refers to the number of coefficients being estimated. For the least flexible model, that would be a simple linear regression. And so the least flexible model is a simple linear regression, which says that y hat I is b0 plus b1 xi. Okay, so here we're estimating two things, two coefficients to estimate, or are estimated. So we say that the degrees of freedom is 2. It's a little bit more complicated than that, the degrees of freedom, but that's where it would end up. Okay, so as we increase the number of terms here, then we would increase the flexibility of the model, but it would also kind of try to incorporate all the information that's in the sample. And that's not always going to help when we apply it to a new model. Okay, and so a more flexible model, or sorry, yeah, a more flexible model might be something like yi hat is b0 plus b, oops, b1 x I plus b2 xi squared plus, I don't know, b3 xi cubed, just kind of going with those. So now I would have a nonlinear relationship, and now I have 1, 2, 3, 4 coefficients, right? So I have a more flexible model, but it might be just describing the training data really well. Right? So here we have 4 coefficients. This is just an example of how we could complicate the model, right? And when we say complicate, we mean we make it more flexible. Okay. And so the problem becomes that, okay, if we have a more flexible model, then, oh, clean this up. Then it might fit the training data really well. How do we communicate that as a measurement? We can talk about the variance. Okay, and so what we can talk about is we consider the expected test mean squared error. The expected test mean squared error, right, for some observation x naught. For some observation x naught. Okay. So the expected mean squared error is going to be y naught, which is of course the actual observation at x naught. Maybe I'll do this at x naught, y naught. Okay, so it's the actual observation in the test data minus the estimated outcome at x naught, and then I want to square it. Okay. This is the expected test mean squared error. We're not going to talk about how it breaks up into this, but what it breaks up into is 3 different components. Okay, so the expected test mean squared error depends on 3 things. Okay, the first thing is the variance of the estimate at x naught. The second part is going to be the squared bias. So it's going to be the bias at f of x naught, f hat of x naught squared. And we'll talk about the bias and what it is, not fully, but we will discuss it, plus the variance of the error term. Okay. So here, the variance is going to be the amount of change that we would see if we applied the same model to a different data set. Okay. So it's the amount of change if the training data changes. Okay. So in general, the more flexible your model is, the more it hinges on the training data, right? So then if you change the training data, then all of a sudden it won't do very well, right? And so there's a lot of variance there. And so in general, a more flexible model means higher variance. I'm gonna add a page here. Not quite ready for those graphics, but just about. Then we're going to talk about the bias squared, or just the bias. The bias can be negative, and so by squaring it, we just get a positive value. Variance, by just the fact, right? The variance can't be less than 0 because you can't have less than 0 spread, right? Variance is a measure of spread, and so variance has to be positive. Bias, once I square it, is also positive. And then I have this irreducible error, the variance of the error term. So this is the irreducible error. The irreducible error we can't do anything about. There's nothing that we can do there because there is always going to be some error that we can't capture with a model. And so that's the irreducible error. So we focus on the variance and the bias squared. So the bias is how different the model is from the actual relationship. We never know what the actual relationship is, so it's kind of mind-boggling, but there is some underlying model that we're trying to estimate. right? And so how far our model is from that actual relationship, that's the bias. How different the model is from the actual relationship. Okay. So in general, right, if we have a more flexible model, then we have lower bias. Okay. So in general, more flexible model, I should say something like a more flexible model or something, but whatever, means lower bias. Remember that we're trying to minimize this whole thing. We're trying to minimize the expected test MSE. So we want to minimize all of this, right? And you can see, okay, if I have a more flexible model, then my variance goes up, right? But if I have a more flexible model, then my bias goes down, right? And so you don't want to have a model that's too flexible, because then it sends you off in two directions, right? You want to find some common ground there. And so that's what we call the variance bias trade-off. We see that as the model becomes more flexible, the variance increases, but the bias decreases. Okay. This is what we call the variance bias trade-off, or the bias variance, I guess. Looking at my notes here, I see it's bias, it doesn't matter. We call this the bias variance trade-off. Okay. So we want to find a model that, well, if we think about what the bias is, well, we want to find a model that looks close to the actual relationship, not necessarily exactly like the actual relationship, depending on how complicated it is, right? But we also want to have the lower variance. So if I apply it to new training data, I want it to be able to perform as well as it did on the original training data, right? And so we need to find models that kind of are some middle ground. And so that's what these graphics are showing here. So if you're looking at them in the textbook, I'll just put them here. This is obviously from the textbook. So usually what we do to illustrate stuff like this, and sometimes it can be a little bit backwards, especially if you're just learning, but usually what we do is we define some relationship. So that relationship is this black line here, and I'm going to zoom in even more because it's hard to see, right? But so this is the actual relationship that we're trying to model. We never know that in real life, right? So it helps because now what we've said is, okay, so here's the actual real life model. And then what we did was we generated random values, right, that would have come from this distribution, right, this model. And then what we do is we try to model this data, right, with different models. So we start off with the simplest form, which is this yellow line, which is just a straight line. Okay, we can see, right, just from, if you kind of squint and only look at the dots, right, then you can see that this doesn't really look like a straight line pattern, right? So you would probably lean towards something more complicated than a straight line, but we can still do it. We can still fit it with a straight line. Okay, but it does what? It increases the bias because, well, it's far from the actual model, which is the black one, right? And then the blue line, let's see if I can find the blue line. The blue line kind of goes like, now it follows it pretty closely here. I can almost not see it. And then the green line just goes around and tries to collect all the data points, and it's trying to adjust for everything that it possibly can. And so it's definitely overfitting, because these characteristics that we're seeing here, they're not necessarily going to pop up again in a new model or a new data set. So what we can do is we can map, as we increase the flexibility, okay, then, so this is the degrees of freedom. We start here at 2. So this is our linear regression. Simple linear regression. Okay. And then these 2 blue dots, and I'll talk about the 2 different lines for now, but later, but these 2 blue dots are the corresponding lines. Okay. Now this dashed line is the actual mean squared error, right? So for this black line, if we were to calculate the mean squared error, then it would be here at 1. Okay. So we can see that, well, the simple linear regression didn't do a good job at all in either case, right? But then what we're going to look at is this bottom set of lines is the training data. Okay, so that's the mean squared error from the training data, which we can calculate. And then here, this is the mean squared error on the test data. Okay. So what happens is, as we increase our flexibility, right? So we're increasing our flexibility. We're only going to look at 3 different flexibilities here, but we can connect them and kind of look at the shape and patterns here. What happens as we increase our flexibility, then we get this drop in mean squared error to a point, but then it starts increasing. And that's because why? Because our variance is increasing, right, faster than our bias is decreasing. Okay, so here, this is the model that would minimize the mean squared error. Minimize mean squared error. Okay. So there's this balance, right, where, okay, there's very little variance in a straight line, because even if we created new points based off of this black line, so we kind of generate new points and then we fit another straight line, it would be relatively similar to this, because it's not really doing a good job. So the variance is very low for this yellow line. Okay, whereas the bias, right, how close it is to the actual curve, well, it's really bad, right? So that would be really high. And the mean squared error is a sum of those 2, right? Plus the irreducible error, right? And so here, that's why these are both so high, right? Because we have high variance. Here, this becomes, they're vastly different, right? Because we've overfit our model like crazy. So we were able to reduce the training mean squared error, right? But then when we went and applied it to the test data, then it didn't do very well at all, right? And that's because we have high variance. Okay. So this is the training MSE is low for overfit model. Yeah. Oops. So then what we could do if we wanted to, why not? Let's see if I can shrink this up. Just a smidge here. So if we have a look at these two different situations, they're the same, we're doing the same thing that we did earlier, right? And so here we have an overall, an actual model that is linear, essentially, right? It's a slightly non-linear, right? But when we fit a straight line, then the straight line does a pretty good job of modeling this relationship, right? And again, we're overfitting the model with this overly complicated model, right? And that's going to minimize the mean squared error on the training data. But then when we go to apply it on the test data, because the test data is not the same, then it blows out of proportion, and that's not what we want. So again, right, we've got this simple linear regression with 2 degrees of freedom. So it's the least flexible model that we can have. And then we increase it to, I'm going to say 3 or 4, hard to say, degrees of freedom here. Maybe 3, I don't know. And it reduces the mean squared error by just a little bit here, right? Slightly down, right? So it does decrease, but then as we increase the flexibility or increase the complexity of our model, then the mean squared error, the test mean squared error starts increasing. So it depends on the actual model of the data, right? So again, here's a completely non-linear relationship. When I go to model it with a straight line, well, my variance is low because it's always going to do a bad job. But the bias is really high because it's so far from the actual curve. Okay? And so what we see again is that kind of the middle ground flexibility with roughly 10 degrees of freedom, it kind of looks like, yields the minimized mean squared error. Okay. We can do this because we have the actual models, right? That's not going to happen in our case, but it illustrates that, okay, you don't want to overfit because there is that trade-off of having something consistent, right? Perform consistently, not necessarily well, but perform consistently versus performing well. So then we can summarize those 3, right? Slightly nonlinear, relatively linear versus really nonlinear models. When we look at the variance in each scenario, which is the orange curve, right? And the squared bias, which is the blue curve, right? You can see that there's like a trade-off here. And then here's the mean squared error. And this is the point that it's minimized at. Okay? And of course, minimizing means that the derivative is 0 and you're at a minimum. Okay, so here, that's what that's saying. Okay. So we look at the mean squared error, and we're just trying to minimize the expected mean squared error in a regression setting. For classification, which is when the y, so the outcome is, maybe I'll say the outcome y is categorical or qualitative. Okay. Well, what we're trying to do is we're trying to classify an outcome, a future outcome. Okay. We try to classify a future outcome. Okay. So we need some measure of error, right? Because in the numerical case, we can just calculate, okay, how far off was I from that value? And that is the residual. And then we square it, and then we take the average of them. And that's the mean squared error, right? And so now we don't have that distance anymore, but we can say if something was misclassified or if it was correctly classified, right? And so we can no longer calculate a difference as we did in the numerical case. In the numerical case, but we can determine if an outcome was misclassified or correctly classified, and that's going to be our error. Okay? But we can determine if an outcome has been misclassified or correctly classified. Punch that down a little bit. Okay. So misclassified means that there was an error, right? So it's not how far off our predictions were anymore. Now we're talking about, okay, was it correctly classified or was it misclassified? And so what we do is we calculate the error rate. The error rate is the sum from I equals 1 to n of I when yi does not equal yi hat, okay, divided by n, because it's an average. I is an indicator variable, and maybe I'll say this instead. I'll do it properly. Where I is an indicator variable, I equals 1 if yi does not equal yi hat, right? So it was misclassified. And it's going to be 0 if yi equals yi hat, right? Which means it was correctly classified. Which leads us to, okay, the error rate is just how many were misclassified divided by however many we tried to classify, right? So really, therefore, the error rate is the number of misclassified divided by the total classified. That seems reasonable enough, right? We've got these categories and I have to guess which category everything belongs in, right? And so one of the options is k nearest neighbors, which is a relatively simple method, but it works most of the time relatively well. And so that's a good thing. Ideally, we would have a Bayes estimator, I think it's called, but we never know the conditional distribution. So I'm going to kind of ignore that for a little bit. It's in the textbook, but that's not going to happen. So some of the options that we actually have available to us, if we don't know the conditional distribution, which we never will, is k nearest neighbors. Okay. So one option for classification is k nearest neighbors. KNN. Okay. So k nearest neighbors, what it does is it just bases the prediction off of what's happening around it. Okay. And so we're able to develop these regions, these kind of classification regions, and we can look at one example like this. So if we're looking at k nearest neighbors, then of course we have to select a value for k. In this case, k is equal to 3. Okay? And we can vary the k, and k equals 1 is going to be the most flexible model. And then as we increase k, it becomes less flexible. Okay? And so if we think about it, then a k of 1, it just looks at, okay, what's my closest neighbor, and then I'll predict that I'm that. Okay. And so instead of looking at, 2 or 3 or 4 neighbors, nearest neighbors, if you're only looking at your first neighbor, your closest neighbor, and then that's your prediction, then yeah, you're going to have this really flexible model, but it doesn't really apply to future data, right? Because those neighbors aren't going to be the same. So let's see here. So for k equals 3, that's a good kind of jumping off point. If we were trying to classify what a point at the x would be, so imagine this whole region, we can predict for every single point in that region within reason, because there's an infinite number of points, but usually we have some sort of grid that we're trying to make predictions for. So we can reduce this to as fine a grain as we want, but something like this is usually fine. Okay, and so if we looked at the x point, then what we do is we go out from the x and we go and we find the 3 nearest neighbors. Okay, all it does is it says, okay, I found 2 blue neighbors and 1 yellow neighbor, right? Or orange or whatever it is. So I predict that this x is a blue dot, right? Because 2 out of 3 were blue. Okay, and that's all the k nearest neighbors does. But we get these regions by doing it for, so notice here, right? We've got dots, 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 dots. And if I go and I pick kind of maybe this dot here, the 3 nearest neighbors would be these guys. So I predict that I am orange here, because I have 3 the 3 nearest neighbors and 2 of those are orange. So I predict that I'm orange. Okay, and then we move to another dot here. Maybe I'll do this. What if I pick a dot here? Okay. If I move out and I find my k nearest neighbors and I want k to be 3, well, I can kind of move out in a circle. So I definitely have this guy in there. I'll have this guy, and then I'm not 100% sure. Oh, I wanted to try to use the looks like that. Okay. So then, so then, oh, sorry, struggling there. Okay, so then I predict that this guy is blue because 2 out of the 3 are blue, and so that makes the blue prediction region, right? And so if I move out to here, this one, which is predicted to be orange, right? If I start a circle here and expand out until I've hit 3 neighbors, so I've hit 1, 2, and 3 borderline, right? Which we can tell, right? And so here I have 1, 2, and I should have expanded this guy just a smidge more. There. Okay, so that's what makes it orange, is because we've got just on the cusp there, but it hit this orange one before it hit this blue one, and so it makes 2 out of 3 orange, and that's what makes the prediction orange. Yeah. So kind of fun, and you can develop these regions. Of course, you would use software, but that's the idea of the k nearest neighbors. A value of k equal to 1 yields the most flexible model. Yields the most flexible model. Okay. So that's just a side note. And then the same idea, right? As the flexibility increases, then our classification would decrease, or our error rate would decrease. I don't know. Lost it. All right. So let's see here. Oh yeah, that's what I wanted to do. I wanted to grab here. This one. Keep it on the same page here. Okay, so 1 over k, as k increases, right? 1 over k gets smaller. And so, yeah. So if we have the training errors and the test errors, then we're trying to level out around this Bayes estimator, okay? Which I'm realizing now we didn't really talk about. So I'll say here's the Bayes error rate, which is the goal, but we can't find it because we don't know the conditional distribution unless we've made up the data, which they have in this course, in this example. Okay. I think that's probably good. We can talk about this all day, but the general idea is that, okay, regardless of the case, right, if we're talking about regression or if we're talking about classification, we need some measure of how wrong we were, right? And so depending on what we're doing, how wrong we were is either in the residuals or it's in the misclassifications. But that's how we pick models, right? Is we're trying to minimize the test error rate. Yeah. You know what? I'm just going to cut this one. It didn't really contribute. So we pick models that would minimize the test MS. Oh, what's going on here? The test means it's like my stupid Apple pencil's running out of ink again. I don't know. Minimize the test mean squared error, or the test error rate. Yeah. So that's kind of the takeaway message. So I think that's good for this section. Next week, I want to do all of chapter 3, so make sure you read ahead. And I'll post the video for the lab. I'm just going to kind of talk about the key points in section 2.3, which is a lab in the textbook. So if you have any questions, let me know. Otherwise, thanks for sticking around and see you Tuesday. Stop this.